Welcome again to Mechanics Applied to Aerospace Engineering. We are going to begin with the second part of this course, and this lecture will be dedicated to the kinematics of rigid bodies. After introducing the rigid body model, we will show that the motion of a rigid body is equivalent to the kinematics of a reference frame and discuss rigid body points. The biggest part of this lecture will be dedicated to the velocity field of a rigid body and also to its acceleration field. Associated to that, we have the concept of the instantaneous axis of rotation and slip that we will see. Finally, we will close the lecture by revisiting Euler angles and with a summary of the main aspects of rigid body kinematics. Okay, so let us get started. Now, in the first part of this course, we introduced the point particle model. We saw that it was a very useful model for many types of problems. Basically, when we didn't care about the attitude or orientation of the object that we were describing or its spatial mass distribution, and we could treat it just as a point. So in those cases, the point particle model is actually quite fine and it works very well. Now, the rigid body model, on the other hand, allows taking into account these two aspects, the attitude and the mass distribution. Now, whenever we say that a body is rigid, okay, the keyword here is rigid, what we mean is that the following kinematic constraint is satisfied. Basically, we say that if we take any 2 points, A and B of the rigid body, for example, those that you see here on the drawing, and we measure the distance between them, no matter how complicated the motion of the body, that distance will remain constant in time. Okay, so basically the vector AB, if you take that magnitude, that is constant over time. Okay. Now this has many consequences. In particular, if you consider 3 points and the angle formed between the segments that join those points, for example AB and BC, those angles also remain constant, right, as a consequence of this constraint. In other words, if this is satisfied, what we have is that the body cannot be deformed. Right, so all the points will move in unison, they will move in the same manner. In other words, well, they will move rigidly. Of course, there are more advanced models in mechanics, okay, and in fact, in other courses of your studies, you will discover deformable bodies, but they are outside of the scope of this course. Now, given that a rigid body can be considered as a collection of a very large number of particles. Okay, you can discretize, for example, this rock over here into many tiny particles, where n is the total number of them. In principle, we would need 3n coordinates to describe the kinematics of this system. Okay, to describe the configuration of all these particles. However, the fact that we have this constraint, okay, the rigid body constraint, which is a very strong constraint, means that in practice we only need 6 coordinates to fully determine the configuration of the system. Okay, and by configuration, when we talk about a rigid body, what we mean is the position of the rigid body and its orientation or attitude in space. All right, so let us discuss how can we describe the configuration of a rigid body, which in general can be very complex. It can have a very complicated geometry. So one thing that we can always do is to define an associated reference frame, SB, which is fixed to the body and moves with the body. Okay, this is what we will call a body fixed reference frame. All right, so how can we do that? Well, it's quite easy. We just have to pick any point of the rigid body. Let's call this point A, and use that as the origin of our reference frame. Okay, so that's half of the problem. In the drawing that you have on the bottom side of the slide, this point is not visible because it's an internal point of the rock. Then let us pick 2 other points of the rigid body, B and C. Again, they can be any 2 points, B and C. The only condition is that they cannot be collinear with A. So in other words, they cannot fall into the same line. And define these vectors, AB, AC, and their cross product. Okay, so these are 3 linearly independent vectors, and we can construct a vector basis with them. All right, and that's the second part for your reference frame. All right, so the reference frame so constructed as you can see, has been defined only from points of the rigid body. The interesting fact about body fixed reference frames defined in this way is that they rotate and translate with the body. Okay, they move rigidly with the body, they move solidarily with the rigid body. They are basically the same thing. Okay. Another interesting thing is that if you are an observer on this reference frame, okay, and you look at one of the points of the rigid body, for example, that one, you will see that it remains stationary with respect to you. Okay, so all the points of the rigid body have zero velocity and zero acceleration with respect to SB. All right. Okay, so this means that we can describe the attitude of the body with the attitude of the reference frame. Regardless how complex the motion of the body, the reference frame remains attached to it. And actually, this is a very convenient feature of this reference frame. Okay. Observe also that the way that we have defined the body fixed reference frame means that we could have defined many others. All right. So actually, there is an unlimited number of body fixed reference frames that we could define. In practice, we just need to define one. Perhaps the most important aspect of all these is that from the kinematics viewpoint, the motion of the rigid body is completely equivalent to the motion of the reference frame. Okay, so we can replace the rigid body with the reference frame, and we just study the motion of that reference frame. Okay, this is an important simplification of the problem because regardless of the complexity, the geometrical complexity of the rigid body, we are always going to do this. We are going to replace them but by a reference frame, okay? And we already know how to study the motion of reference frames. We studied that in previous lectures when we were talking about the relative motion. So we know that we basically need to provide the information about the motion of the origin of the reference frame and the motion of the vectors of the basis, what we call the attitude of the reference frame. Now, I've been talking about rigid body points, but I didn't really define what they are. So what is a rigid body point? In essence, it is any point P of the body that travels with the body fixed reference frame. Okay, so in other words, the relative velocity with respect to SB and the relative acceleration with respect to SB are equal to 0 at all times. All right. Well, here it is important to notice that this definition is quite wider than material points of the rigid body. Okay, so imagine that you have this body here and a body fixed reference frame attached to it. So clearly this point on the rigid body is a body point. Okay, it's a material point of the body, but also any other point outside of the rigid body, as long as it moves in the same fashion attached to the reference frame. Okay, for example, that point on the y-axis is also considered to be a body point. All right, and this is an important idealization of the problem. We can remove for our purposes the boundaries, the material boundaries of the rigid body, and just consider all the points of the space that is associated with this reference frame, okay, and move with the reference frame as rigid body points. Okay. Now, later on this course, we will have a case of ambiguity where it is important to denote that a point A belongs to a rigid body. Okay, by saying that a point belongs to a rigid body, we are basically saying this, okay, that its velocity and acceleration with respect to a body fixed reference frame are equal to 0. So, in order to avoid ambiguity between a fixed point of a space A and the body point that happens to be on top of that point at some instant of time, we will use this nomenclature. Okay, so usually we will not need to do this. Okay, we will only use it when necessary to avoid the ambiguity. All right, this is important because, as we will see, the velocity of the point A and the velocity of the rigid body point that happens to be on top of point A, what we call A parenthesis B, will be different. Okay, so even if their position coincides, the velocity and the acceleration can differ. All right, so let's just keep this on a side note for now, and we will come back to this nomenclature later on this course. Okay, so let us discuss the velocity and acceleration field of a rigid body. Now, if you remember, the condition that a point P is a body point, by virtue of the rigid body constraint, means that its velocity and its acceleration in the reference frame that is body fixed, okay, in reference frame SV, is equal to 0. And that's true for any point P of the rigid body. So if we start with the expressions for the velocity and acceleration that we learned about in the lecture of relative dynamics, we have the possibility of using them to relate the velocity of a point P of the body as seen from reference frame S0 and as seen from reference frame SB, all right? But now, since the velocity of that point in the reference frame SB is equal to 0, we can remove that part. Similarly, in the case of the acceleration, the acceleration of the point P with respect to the rigid body is 0 because it's a point of the rigid body, and also the Coriolis acceleration is 0 because its velocity is 0. So if we clean this up a little bit, what we have is these two expressions, all right? Now, of course, AP is the vector that goes from the origin of our reference frame to point P, and we can call it also RPB, okay? Now, these two expressions are very important. They are the velocity and the acceleration field of the rigid body. Especially the first one is relatively important to us, right? Observe that we can regard the right-hand side of these expressions as a function that assigns a value of the velocity and the acceleration to each point of a space. Okay, if we consider each point of a space a point of the rigid body, then this is a function that assigns a velocity vp0 to each point RPB. Okay, so provided RPB, the position of the point in the reference frame SB, you can get from this expression what it should be its velocity if it is a point of the rigid body, of course. And similarly for the expression of the acceleration. Now, if we put our focus on the first expression, the velocity field, we observe that the instantaneous velocity of any point P of the rigid body can be thought of or can be decomposed as two terms, all right? We have on the one hand the velocity of an arbitrary point A, okay, the point that we have chosen as our origin for this equation, okay, this one. And then another term which represents a rotation about that point with angular velocity omega v0, all right, the second one. So we can always think of the velocity field in those terms. We have the velocity of one point that acts as the reference, and then about that point we have a rigid body rotation. In particular, a particular case of motion, it happens when the angular velocity is equal to 0. Okay, then in that case, the second term disappears, and we just have the quality that the velocity of P, whatever P is the velocity of A. All right, for every P of the rigid body. This is what we call a pure translation with respect to S0. Okay, and it can happen that this is only true at a particular instant. If the motion is accelerated, then this can change at a later time. So that's why we use the word instant or instantaneous when we talk about this. Okay. Now, observe also that if you project this equation, the equation of the velocity field, in the direction of omega, okay, if you dot multiply by omega v0, then the last term, which is perpendicular to omega because it is a cross product with omega, that one does not contribute. Okay, so what we have is this equation. Okay, here I have defined the unit vector e omega, which is a unit vector in the direction of omega. All right. So this is what we call the projection of the velocity of point P and point A in the direction of the angular velocity vector. All right. And from this equation, we can see that whatever the point that we pick, okay, whatever the point P is, the component of the velocity of P in this direction is always the same. Okay, it's the same as the velocity A projected in this direction. We will call this component V parallel. All right, and we will call this component the slip speed. All right, or the parallel speed. In fact, this offers the possibility of decomposing the velocity of any point P in a very interesting way. On the one hand, we can split the velocity into a term that is parallel to the angular velocity vector. Okay, here we got the slip speed and multiplied it by the unit vector e omega to get a vector, the v parallel vector. Okay, and this vector is universal for all points of the rigid body. At that instant, they all share the same parallel velocity. Okay. The only part of the velocity that depends on the actual point P that we have selected is the other term, the term that is perpendicular to the angular velocity vector. In the particular case where the slip speed is equal to 0, we call the motion a pure rotation at that instant with respect to S0. Okay. Now, if we have a pure rotation, there are a set of points in the rigid body which have 0 velocity. Okay, those points where both the parallel velocity, which is 0 provided this condition, and also their particular perpendicular velocity is equal to 0. In that case, we have points that have 0 velocity, right? The collection of those points with 0 velocity is what we call the instantaneous axis of rotation, and it is a straight line in the direction of omega v0. Okay. In essence, in that case, we have a motion that looks like this. All right. All the points of the rigid body are rotating with respect to a line, which in this case is perpendicular to the drawing. And the points that are closer to this line have a smaller velocity magnitude than those that are farther away. Okay. Now observe that in general, the instantaneous axis of rotation may be outside of the material boundaries of the rigid body. Again, this is not a problem. Remember that what we will do in practice is always to replace the rigid body with a body fixed reference frame. All right. So the material boundaries don't really matter for our purposes. Another thing that we can do with the velocity field equation over here is to project it in the direction of vector AP. Okay, so again, we take the dot product of this expression and we observe that the last term does not contribute because it is perpendicular to AP. So basically we get this result over here. All right. Now, what does this mean? Well, it means that if we have a rigid body and we have a point A and a point P, okay, they may have whatever velocity. Okay, for example, point A may be moving like that, and point B may be moving like that. But if we project their corresponding velocities along the line that joins them, the segment that falls along that line has to be equal in length. Okay, so that component has to be identical for the velocity of A and the velocity of P. And this is just a consequence of the rigid body constraint. Okay. Now, one interesting thing that we can do with the equation for the velocity field is to try to find out what is the motion of the rigid body if we have enough information. All right. So this can be done in many different ways depending on the information that you have, but the velocity field equation is the expression that you want to use in these cases. So imagine in particular that you have 3 points, A, B, and C, of which you know their position and you know their velocities. All right. In the drawing, these would be the 3 points. The only condition that we are going to impose for this particular exercise is that the points are not collinear, okay, same as before. So you can, first of all, use these 3 points to construct your reference frame SB, okay, as we saw before. And you can also use them into the equation. You can place the data that you have into the equation of the velocity field to find out the missing information that you don't have. So in this case, the only vector that you don't know is the angular velocity vector. Okay, so you can write down these two equations, which are particularizations of the velocity field expression, joining the velocity of A and the velocity of B, and the velocity of A and the velocity of C. Okay, and with this you get enough equations, actually more the equations that you need to determine the components of the angular velocity vector. Right, you can write them down in whatever basis you are working, but you can name them like A, B, and C. All right, and you just have to get from these equations a linear system of equations from where you can compute A, B, and C. All right. The fact that you have more equations than necessary to determine these three parameters poses a problem. Okay. Basically, the other equations that you are not using have to be compatible with those that you are. All right. Otherwise, you get data about the motion of the rigid body that is not consistent. So imagine, for example, that I have these 3 points in the drawing, A, B, and C, and I get information that point A is moving like this, point B is moving like that, and point C is moving like that. Well, clearly that cannot be, because that is not consistent with the fact that the 3 points belong in the same rigid body. All right, if the points move like that, clearly the distance and the angles between them are not going to be conserved. All right, in that case, if I use such data on these two equations, well, clearly I will get something that is non-compatible. So this can also allow you to check whether the information that you have about a rigid body, imagine that you have several measurements of the motion of different points of a rigid body at some instant, you can check that this is a rigid body or not, or maybe some of your sensors are wrong or something like that. Perhaps the important bit here is that if we want to talk about the velocity field of a rigid body, okay, which is an essential part of the kinematics of the rigid body, we need to determine two vectors. We need on the first hand, we need the velocity of one point. Okay, any point will do, but we need one point of which we know its velocity, and then we also need to know the angular velocity. All right. So if we don't know one of these two vectors, we have to find them, and we need to have enough information to use the velocity field expression to find the missing information. Okay. So we have talked about pure translation and pure rotation, but the most general type of motion that you can have is both things at the same time. You can have a rotation with angular velocity omega, and then a translation parallel to this direction. Okay, and this is important. If you try to construct a more general motion with a translation that is not parallel to omega, the part of that translation that is perpendicular to omega, you can absorb it in the rotation. Okay, in the rotational type of motion. Basically, adding a translation perpendicular to omega just means that we are moving the instantaneous axis of rotation, but we are not changing the fact that that is pure rotation. Okay, if we want to have this type of general motion, we need a rotation and some parallel translation parallel to omega. And this type of general motion is what we call sometimes a screw motion, because it reminds us of the motion of a screw as we put it into a piece of wood, for example. So what does it look like? Well, in essence, if we look it in the direction perpendicular to omega, like in here, we just see the rotational part. Okay, so again, we have an instantaneous axis of rotation, and all the points in the body are moving around it like that. But if we look at the motion from a different direction, this is what you have on the drawing on the right. Okay, what you see is that all the points, on top of doing that rotational motion, they are translating in the direction parallel to omega with the same parallel velocity. Okay, remember that that part of the velocity is always the same for all points. We can always decompose the velocity of a point P of the rigid body as a parallel part plus a perpendicular part. And only the perpendicular part depends on the specific point. Okay. Here you can see that that perpendicular part corresponds with the rotation, okay, and the parallel part corresponds with the slip, all right, or with the advance of the screw motion. Whenever we have this combined motion, the screw motion, the instantaneous axis of rotation is called instantaneous axis of rotation and slip. Right, and it is defined as the locus of points which have the minimum velocity of the rigid body. Observe that since this part of the velocity is universal for all the points of the rigid body at that instant, and only this one depends on the particular point, the minimum velocity is precisely the parallel velocity. Okay, so all the points on the instantaneous axis of rotation have the minimum velocity, which is just the parallel velocity. Okay, any other point on the rigid body has, on top of this parallel velocity, the rotational part, which is the perpendicular velocity VP perp. Okay, and again, just as before, the direction of this axis is the direction of the angular velocity vector. So let us look at how we can find, how can we locate this instantaneous axis of rotation and slip in space. So in order to do that, we are going to use again the equation of the velocity field of the rigid body. We are going to find the point I, all right, that belongs to the instantaneous axis of rotation and slip. Well, basically, the condition that we have to apply is that its velocity is minimum. In other words, we have to equate its velocity in the expression with the parallel velocity. Okay. Now, what we are going to do is to cross multiply this equation by omega b0. So if we do that, we get this equation. All right, so here we get a double cross product. Okay, and on the right hand side, we get omega b0 cross v parallel. Okay, now clearly this term is equal to 0 because the parallel velocity goes in the direction of omega. So this cross product is equal to 0. If we apply this vector relation to expand the double cross product, okay, we can rewrite this expression as you see on the slide. Right? So this term is the same as before, and these two terms are the ones that come out of the double cross product. And on the right hand side, I have already put a 0 because that is what we had when we realized that omega cross v parallel is equal to 0. Okay. Now this expression is the one that allows us to find any point I on the instantaneous axis of rotation and slip. Okay, so this is an equation that is satisfied by, for example, this point I prime. Okay, if you put into that equation the vector I prime, it will satisfy this equation. All right. So since we want to determine the direction and the position of the rigid of the instantaneous axis of rotation, and its direction we already know, it is the direction of the angular velocity vector. All that we need to know is the position of one and only one point of this axis. All right. So in order to simplify our lives, one thing that we can do is to find the easiest point. Okay. So for example, let us try to get this point, the point such that if you take the vector AI, that vector will be orthogonal to the instantaneous axis of rotation. Okay. So what happens if we select that particular point? Well, in that case, since AI is perpendicular to omega b0, this first term that comes out of the double cross product will vanish. Okay, and that's okay. This is perfectly fine. We are just looking for one point of the instantaneous axis of rotation. So let us just pick the simplest of them. All right. So this is the equation that gives us precisely that point. Of course, we can rearrange this equation to solve for the vector AI, which gives us the position of the point that we are looking for. All right. Observe that this procedure is identical whether you are looking for the instantaneous axis of rotation and a slip, okay, when you have a slip, and when you don't have it. In that case, well, you just start with a 0 on the right-hand side, okay, but it doesn't change anything else. In that particular case, when the parallel velocity is 0, we drop the slip surname of this axis, and we just call it the instantaneous axis of rotation. All right, so I think this is a good time to look at a simple example. So imagine that we have a rigid body. In this case, happens to be an airplane, and we have 3 points, G, A, and C, of which we know the position and velocity in some reference frame S0. The center of mass happens to be point G, but this doesn't have any relevance for this particular problem. So we have this information about a particular instant of time of the motion of the rigid body. And we want to know what is the angular velocity of the body at this instant, what is the parallel velocity, if any, the slip velocity, okay, the type of motion that this aircraft is doing, and what is the instantaneous axis of rotation and slip. All right, so these are the things that we want to know. So the most useful piece of information is to find omega, because once we have that, finding the parallel velocity means just taking one of these velocities, any of them, and projecting that along the direction of omega. And also finding the instantaneous axis of rotation requires having the angular velocity. Okay, so in order to find it, we are going to apply the expression of the velocity field of a rigid body to relate pairs of points. Okay, so for example, if we take point A and point G, we can write that the velocity of A minus the velocity of G in reference frame 0 is equal to omega v0 cross the position of A minus the position of G. Okay. Similarly, we can write a similar equation, but relating point C with, for example, point G. All right. So we will have something like this. All right. So from these equations, we need to find the components of omega, and that way we can determine what it is its value at this particular instant of time. So let us just call these components with generic names, for example, A, B, and C. Okay, and I have chosen to work in basis 0 because I have all the information in that basis. Okay, here in the statement of the problem, the information doesn't have the subindex, but this is the basis 0. All right. So I just need to work out these two equations. So starting with the first one over here, the difference between the velocities of A and G is minus 2I0 minus J0 plus 3K0. Okay. And on the right hand side, I have the cross product, which I can write as a determinant, A, B, C, and the 3 components of the difference of the position between A and G. Since the position of G is 0 at this instant, that makes this difference particularly simple. We just have to write the position of A. So this is minus 1, minus 2, 0. Okay. So if we solve this cross product, what we have is 2CI0 minus CJ0 and plus 2A plus B K0. Okay. From this vector equation, we can basically separate 3 scalar equations. All right. So we can equate the component along I, the component along J, and the component along K. and we obtain the following equations. So we will have minus 2 equals minus 2c, minus 1 equals minus c, and 3 equals 2a plus b. All right. So clearly, the first two equations are telling us the same thing. If you remember, I mentioned that we had a surplus of equations. We actually will get 6 scalar equations for 3 components of the angular velocity. So this is something expected. What we demand from these extra equations is that they have to be compatible with the rest of them. Okay, so in this case, we see that they are compatible. From here, we just find that C is equal to 1. Okay, the other equation, we have to save it for later because we don't have enough information yet. So let's do the same thing with the second equation here. So we have that the velocity difference between C and G is I0 minus 5J0 plus 4K0. And we have to equate that to the determinant of ABC and the difference of the position of these 2 points. Again, the position of G is 0, so we just have minus 4, 0, 1. Okay, so if we solve for this determinant, we will find BI0. Okay, then we have 2 terms for J0, so that is minus 4C minus A J0. And finally, we have 4bk0. Okay, so there you go. From here, we find again 3 scalar equations. We just have to separate the components of each of the vectors of the basis, and we find 1 equals b, minus 5 equals minus 4c minus a, and 4 equals 4b. All right, so from here, we clearly see that b is equal to 1. Okay, so let us write here our solution. We had from before that c was equal to 1, and from the remaining equations, we also see that a is equal to 1. All right. The rest of the equations, we see that they are compatible, so there is no problem. This is consistent with the rigid body constraint. So in principle, this is the velocity field of the rigid body. And the angular velocity ends up being I0 plus J0 plus K0. Okay. Okay, so we have just found the value of the angular velocity. The next thing that we want to do is to check whether if in this instant of time there is any slip velocity or not. Okay, that will allow us to determine whether this is a pure rotation, because we know that already there is that there is some rotation, we have some omega different from 0, or if we are in the general case where we have some rotation and some slip in the parallel direction. So let us find out this parallel velocity. Okay, for this we can use any point that we want. So let us use, for example, point A. So we just have to project that velocity in the direction of omega. Okay, since we want to find out this in a normalized way, we will divide by the magnitude of omega. And since we want this to be a vector, all right, we will multiply again by omega vector. Okay, we will divide again by its magnitude. So we get something like this for the expression of the parallel velocity. All right. So if you take the dot product over here, you find, if I am correct, you find something like 6. Yeah, the value of this dot product is equal to 6. Okay, and then the magnitude of square of the angular velocity, which was 111, is equal to 3. Therefore, the parallel velocity is different from 0, and actually it is 2 times I0 plus 2J0 plus 2K0. Okay, so we conclude that since we have omega v0 different from 0 and a parallel velocity different from 0, we are in the general case, okay, what we call the screw motion. All right. The last thing that we are going to do with this example is to find out the position of one point in the instantaneous axis of rotation and slip. Okay. So remember that there is somewhere this line, okay, with respect to the rigid body. And we already have 3 points. We have G, A, and C, right? And we just want to find a point on this instantaneous axis. So rather than finding any arbitrary point, we always try to look for the perpendicular foot to one of the points that we already have. Okay, this is the point that we are going to call I. The advantage of looking for this point that satisfies this condition is that the expression for it is simpler than if we pick any other point of the instantaneous axis. Since the instantaneous axis is given by providing one point and the direction vector of the axis, which is omega v0, and this already we have, we just have to find this particular point. Okay. All right. So let us use the expression that we found in one of the previous slides. The position vector from G to I is given by the cross product of the angular velocity times the velocity of point G, and then we have to divide by the square of the magnitude of the angular velocity. Okay, since the position of G is equal to 0, this vector can also be written as the position of I in reference frame 0. Okay, so you just have to take this cross product, which we will write here in the margin. So in this case, we already know the value of the angular velocity, and the components of the velocity of G are this. Okay, so if you work this out, you get minus 2 I0 minus 4 J0 minus 2 K0. Since the omega v0 square is equal to 3, we can finally write this as minus 2 over 3 I0 plus 2 J0 plus K0. Okay, so this gives you the position of one point on the instantaneous axis, and that's it. Okay, now it's important to realize that everything that we have done in this example refers to a single instant of time. In the next instant of time, the angular velocity vector may have changed, the position of the instantaneous axis of rotation may be a different one. All right, so everything that we do in this type of exercises refers to a particular photograph of the motion of the rigid body. Okay. To conclude this lecture, let us revisit the Euler angles. Right? So remember that Euler angles were a very useful tool to determine and describe the attitude of a reference frame. Well, since we can basically replace a rigid body with a body fixed reference frame, this is the trick that we will use to talk about the attitude of a rigid body as well. We will basically introduce 3 Euler angles, right? Usually by the name of psi, theta, and phi. And we will have 3 simple rotations in a prescribed order to go from the orientation of our reference frame S0, wherever we are working, to the reference frame SB of the rigid body. Okay. So remember that when we talk about Euler angles, it is important to mention what are the type of Euler angles that you are using. In previous lectures, we saw in particular the 3-1-3 Euler angles and the 3-2-1 Euler angles, but remember that there are others as well that you can define. Some additional aspects about Euler angles that we didn't cover on previous lectures are the following. Well, first of all, you should realize that Euler angles have some defects. Okay, usually we can live with these defects and they are not a problem, but you should be aware of them. For example, whatever attitude you are trying to describe, you can get there with at least 2 different types of rotations. All right, so for example, you can pause the video and check that if you have 3-1-3 Euler angles, this rotation and this rotation are equivalent. You will end up with the same attitude of the reference frame. The other aspect that wasn't mentioned on previous lectures is that in addition to this, some specific attitudes are singular with respect to some type of Euler angles. All right, and this happens when the second rotation makes the first and third rotation axis to coincide in inertial space. Okay, in that case, the angles psi and phi are not well defined, and only the sum is correctly defined. Again, this is not an issue when we are using Euler angles just to describe the attitude of a reference frame, but it means that the solution of your Euler angles for that particular attitude is not unique, and actually if it's singular, you have a continuum of possible values of the Euler angles that give you the same attitude. All right, and that can have some problems when integrating and when working numerically with Euler angles. So in particular, just to show you what I mean with this statement, okay, the fact that the second rotation leaves the first and the third axis of rotation identical, imagine that we start with this reference frame, okay, x0, y0, z0, and we perform a first rotation about the vertical axis of an angle psi. Okay, so you end up with x1, and y1, and this is the same as c1. So imagine now that your second rotation associated to the angle theta is equal to 0. So you basically have theta equal to 0 and you don't rotate anything. Okay, then that means that this is equivalent to x2, y2, and c2. All right, so in principle that's not a problem. But now when you want to do the third rotation, you are going to rotate again about this vertical axis. Okay, and for an observer outside of this whole thing, that line coincides in space with the first axis of rotation. So when you do that, you will end up with an additional rotation that looks like this. Okay, and you see that in this case, it doesn't really matter how much you rotate it with the psi angle and how much you rotate it with the phi angle. The only thing that matters is that the sum of the two is the same value. Okay, so if that is whatever angle delta, as long as delta is the same, it doesn't matter how you split the rotation between these two angles, the end result is the same. Okay, so this happens because the second rotation has aligned in space the axis of rotation of the first and the third rotations. All right, and for 3, 1, 3 Euler angles, this happens whenever theta is equal to 0 or equal to pi. For other types of Euler angles, the singularity appears in different values of theta. Okay. Okay, so as a summary of this lecture, since we have seen that we can replace any rigid body with a body fixed reference frame, okay, we conclude that a free rigid body has a total of 6 degrees of freedom. Okay, we need to provide 6 variables, 6 coordinates to completely determine its configuration. All right, and for a rigid body, the configuration is the sum of its position, the position of one point, for example, the origin of the reference frame that we are using, and its attitude. Okay, so how can we do this? We can do it in many different ways, of course, but a common choice is to spend 3 coordinates to determine the position of one point A of the rigid body. Okay, we will see in later lectures that an interesting choice of point A is to choose the center of mass of the rigid body. Okay, that's what we usually call G. The other 3 coordinates would be used to determine the attitude of the rigid body. Okay, and this can be done, as we have just seen, with Euler angles. Of course, once you have done this, the most natural choice is to define your body fixed reference frame with the point A that you have selected here and with the vector basis that comes out of the rotations associated to the Euler angles, of course. Okay. Now, I want to emphasize this. Remember that this is not the only choice. Instead of using Euler angles and 3 coordinates for the position of a point, there might be other possibilities depending on the problem, but this is quite general, quite common choice, and we will see it at work in many problems. Okay. When we talk about the coordinates of the point, by the way, they don't have to be Cartesian coordinates. Okay, so we may use, for example, spherical coordinates or any other type of 3 parameters that allow us to locate a point in a space. Finally, when we talk about solving the kinematics of a rigid body, okay, or writing down the kinematics expression of a rigid body, what we mean is to provide the following vectors. Okay, so basically we care about the position, velocity, and acceleration of one point. Okay, so for example, the point A that we were talking about here, all right, and the attitude of the body, which we can relate to the 3 vectors of the basis. Okay, and then it's angular velocity and angular acceleration vectors. So this is in essence what we are looking for. All right, we have to write down all these vectors as a function of only those 6 coordinates that we have selected, 3 coordinates for one point and 3 Euler angles, for example, and of course their derivatives. Okay, so as long as we are able to write down those expressions in a general way, then we have the kinematic expressions that we are looking for the rigid body. So that's it. Thank you for your attention and see you next time.